Okay, it is 2 o'clock, so I am going to get started now. Good afternoon, everyone, and thanks for joining us on our call today. My name is Nicole Van Wert Quincy from Transcat, and I'm going to be your moderator this afternoon. Our webinar topic today is Power Quality Basics 101, and it's being presented by Jason Honeycutt from Megger. Jason's been in the electronics field since 2003 when he graduated from Lincoln Technical Institute in Allentown, Pennsylvania for electronics servicing. He has been with Megger for 10 years. His primary focuses have been in high voltage and power quality, and he is currently Megger's application engineer for their power quality products line. We expect today's presentation to last roughly 30 to 40 minutes, and then we'll answer any questions that have been submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded, so you will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. So at this time, I'm going to turn the presentation over to Jason.
Hello, everybody. As Nicole said, my name is Jason Honeycutt. I'm the applications engineer for Megger's power quality line. Power quality is the concept of powering and grounding your sensitive equipment in the manner that is suitable to the operation of that equipment. So basically, if your equipment does not operate properly due to the power it is receiving, then that would be a power quality problem. So today the modern grid is changing. Solar and wind sources provide inconsistent power. As the clouds increase, solar power is reduced. Same as wind. When it slows down, the power is reduced. This leads to rapid changes in the voltage. The reduction of coal plants is also causing more load on other sources, such as nuclear. In the past, transmission lines would typically be running at 50%. With the new increased loads on other sources, transmission lines can be loaded up to 95%. This greatly reduces the reliability. As electric vehicles are also increased, smart grid grows, and the peak loading times will change. All of these things will provide challenges to the modern grid and power quality. The smart grid reduces the power quality issues. It will not. It actually just increases the grid reliability and communication through the sources, not the actual power being delivered. As new technologies are introduced, solar and these other types, we will always be creating new power quality challenges. So some of the things we'll talk about today will be your under voltage, over voltage, dips and sags, swells, transients, unbalance, flicker, harmonics, and RVC, or rapid voltage change. An under voltage is a decrease in the RMS voltage less than 0.9 pu, or percentile unit, for longer than 1 minute. They are usually between 0.8 and 0.9 pu, and typically caused by load switching on or capacitor bank switching off. And they will continue until the voltage regulation equipment on the system can bring it back within tolerances. Keep in mind, overloaded circuits can also result in under voltage. Having too much load on an individual source can create under voltage on all the loads on that source. An overvoltage is an RMS increase in the AC voltage greater than 1.1 pu during longer than 1 minute. Typically, they would be 1.1 pu to 1.2 pu, and result in caused by load switching, such as large motors, switching of cat banks, even poor voltage regulation capabilities in a system, incorrect tap settings on transformers and solar panels, because they turn off and on real fast due to the cloud cover, which can create that. Voltage sags and swells are the most common power quality events. Unfortunately, they cannot be prevented on the power system. Simply as impedance changes throughout the day, so will the voltage. Even instantaneous short duration sags can cause the process shutdowns requiring hours to restart. And when you have a manufacturing process that is time dependent, a failure could cause an entire run to be discarded and the financial losses to be significant. Voltage swells are also the most common problem or cause of tripping breakers. Common causes of the voltage sags would include voltage change, like when you turn on a motor and rush currents, as well as inadequate wiring. Voltage swells would include load switching, utility faults, or even neutral connections being damaged or loose. As the load turns on, the impedance decreases, which increases the current, which can cause a drop in the voltage. As the load turns off, the impedance increases, which can lead to a swell in the voltage. Another cause would include the voltage for the equipment coming into the building. So something like a piece of equipment that should be running on 230 volts being fed from a 208 volt line or vice versa. You always want to check that your equipment voltage is correct because you may find that a PQ analysis is not required. So on a single phase system, a voltage dip begins when the RMS voltage falls below the dip threshold. For a Class A unit, it is measured every half cycle on a sliding scale, and the event ends when the RMS voltage is equal to or above the dip threshold plus the hysteresis. For example, if the dip or sag threshold is at 100 volts and the hysteresis is set to 2%, then the dip or sag will start when the RMS value falls below 100 volts. The event will not end until the value rises above 102 volts. Hysteresis helps prevent the reporting of false events due to measured voltages being too close to the event threshold voltages. On a polyphase system, the sag will begin when the RMS voltage of one or more of the phases is below the dip threshold, and it does not come back up until all the phases are equal to or above the dip threshold plus the hysteresis. The dip and sag detection on a polyphasor system is the same as a single phase system, except all three phases need to be within the threshold plus hysteresis, and the standard value for hysteresis is 2%. Class A swell detection on a single-phase system would begin when the RMS voltage rises above the swell threshold, and the swell will end when it is equal to or below the threshold minus the hysteresis. Same goes on a polyphase system. It would need to go below the RMS voltage on one or more of the channels rises above the swell threshold and will not come back up until all phases are equal to or above the threshold minus hysteresis voltage. Let's talk about transients. Generally, there are two types of transients, transient over voltages. We have low frequency transients with frequency components in the few hundred hertz region, typically caused by capacitor switching, and they are known as oscillatory transients, and high frequency transients with frequency components in the few hundred kilohertz region, typically caused by lightning and inductive loads, known as impulsive transients. Transient voltages can cause degradation or even immediate dielectric failure in equipment. The high magnitude and fast rise time contribute to insulation breakdown in equipment, like motors and transformers. Even repeated lower magnitude transients to equipment can cause slow degradation and eventual insulation failure. So we can see on this picture here that transients are like wires are like capacitors. Both capacitors and wires have two conductors separated by an insulator. This capacitance path provides a path for the transient pulse. And if the transient pulse has enough energy, it will damage that section. That can be understood by this capacitance reactance formula. It can be seen that the value of the frequency, if the value of the frequency increases, the lower the reactive capacitance will be, and therefore the lower the impedance path. And the lower the impedance path, the more current will flow and will break down the insulation. Lightning is a major cause of transients because a bolt of lightning can be 5 miles long and reach 20,000 degrees C. Lightning strikes, or the electromagnetic fields they produce, can induce voltage and current transients in the power lines. These are typically seen in unidirectional transients. Although lightning is a major cause of these types of transients, another cause would be equipment switching. When capacitor banks are switched on, there's an initial inrush of current. This will lead to low frequency transient that will have a characteristic ringing sound. These types of transients are referred to as oscillatory transients, and they can cause equipment to trip out and UPS systems to turn off and on erroneously. Since UPS banks are made to switch quickly, if they are too sensitive, these transients will cause them to turn off and on multiple times per day. Typically, turning down the sensitivity on a UPS will fix this issue. EFTs, or extremely fast transients, have rise and fall times in the nanosecond region, typically caused by arcing faults like bad brushes in a motor, or they are rapidly damped out even with a few meters of distribution wiring. Most equipment these days are made with standard line filters, which are made to remove these EFTs. These problems will typically be in areas with short cable runs, such as offshore oil platforms, mines, and solar. Unbalance is another phenomenon we see in power quality, and that's the condition of a polyphase system in which the RMS values of the line voltages or the phase angles between consecutive line voltages are not equal. This can either be due to the magnitude variations between phases or phase angle variations. Voltage unbalance more commonly emerges in individual customer loads due to the phase load imbalances, especially where large single-phase power loads are used, such as an arc furnace. As you can see in this picture, a small amount of unbalance on the phase voltages can cause a large unbalance in the phase currents. Unbalanced voltages can also affect the equipment, cause heating effects, and cause them to die or fail prematurely. and have to be replaced. So voltage unbalance can be described as a set of symmetrical components. In a balanced three-phase system, all the line to neutral voltages would be equal in magnitude, and the phases would be displaced from each other by 100 to 120 degrees. So any change in that would cause unbalance in the system. Flicker is another phenomenon that we see, and it is directly related to the human perception and sensitivity to incandescent light bulbs. It is not a general term for voltage variations. It just refers to how we visually see the rapid variations in the lighting. So humans can be very sensitive to the light flicker. It can cause headaches or even nausea. Lighting variations at different frequencies are perceived differently by the human eye. So it may affect one person, may not affect another one. This figure illustrates the level of perception of a light flicker from a 60-watt incandescent bulb. The sensitivity is a function of the frequency of the fluctuations, and it depends on the voltage level of the lighting. The human eye is most sensitive to the incandescent lamp flicker at a rate of 8 Hertz. At this rate, a very small change in the voltage is required to create a perceptible change in the illumination. As frequency goes up or down, a greater change in the voltage is required to create that perceptible change in illumination. Anything above 30 Hertz, the human eye will not perceive the flicker changes. So, as of now today, flicker is measured using the IEC 61000-4-5 method. In that method, they take the instantaneous voltage and they compare it to the rolling average voltage, which will then, and the deviation will then be multiplied by a value that's in the weighted curve. This curve is based on the sensitivity of the human eye at 120 Hertz, 120 volts, 60 Hertz, or 230 volts, 50 Hertz. The curve cannot be used on any other lighting because of this. So there's two ways to express flicker. We have short-term flicker, or PST, which is calculated on a 10-minute interval, and long-term flicker, or PLT, which is calculated based on the PST but on a 2-hour interval. So the basic criteria is simple. If the PST is less than 1.0, the flicker levels are good. If it's greater than 1.0, it could be causing irritation. So in short, if the PST does not exceed 1.0, then the amount of light flicker from the incandescent lamp should not be perceivable. The same would be true for PLT, or long-term flicker, at values below 0.8. Now, harmonics are a sinusoidal component of the periodic wave that have frequencies that are multiples of the fundamental frequency. So here in the United States, the fundamental would be 60 Hertz. The second order would be 120 Hertz, third order 180 Hertz, and so forth. Harmonics cause a lot of problems with overheating on motors and transformers, and even electronic failures. The overheating can cause premature failures to your equipment. So the IEEE 519 defines a harmonic as a component of order greater than one of the Fourier series of a periodic quantity. The IEC 61000-4-30 defines the harmonic frequency as a frequency which is an integer multiple of the fundamental frequency, and defines the harmonic component as any of the components having a harmonic frequency. So we know linear loads such as incandescent light and motors draw current throughout the waveform evenly, and nonlinear loads like switching power supplies draw current only at the peaks of the wave. It is these nonlinear loads that cause the harmonics. Nonlinear loads that draw power at the peak of the wave create more efficient power sources, but insufficient enough in quantity, and create the harmonic issues. Typically, current harmonics will not propagate through a system. Voltage harmonics will, as they pass through the transformers. When nonlinear loads get high enough, they can cause the harmonics in the voltage. In the example we see to the right, we see flat topping. The current draw at the peak of the wave is too high for the transformer to deliver. Thus, the voltage at the peak of the wave is reduced. So harmonics can be characterized based on their order. We have odd harmonics, which are typical. Even harmonics are not typically seen and can be an indication of faulty equipment. Since triplets do not cancel out, they create very large neutral currents. Neutral wires used to be smaller than the main wires. Now we see in plants neutral wires are typically larger than the main wires, and that is to accommodate for the potentially high neutral currents. Harmonics can also be characterized into different sequences based on their rotation of their magnetic field. We have positive sequence harmonics. Their magnetic field that they create are in the same direction of rotation. Negative sequence harmonics develop magnetic fields in the opposite direction. This reduces torque and increases the current load for motor loads and causes overheating. In zero sequence harmonics create a single phase signal that does not produce a rotating magnetic field of any kind and can increase the overall current demand and generate heat and cause your equipment to fail prematurely. So in a three-phase system, the fundamental currents will cancel each other out and add 0 amps into the neutral line. But zero sequence harmonics, like the third, will be in phase with the other currents of the three-phase system, and they will add together and lead to high neutral currents, as you can see on that graph there. On this graph, it shows the positive, negative, and zero sequence harmonics run in sequential order. It will start positive, negative, and then zero, and repeat. Since the fundamental frequency is positive, the second would be negative, and the third would be zero, and again, repeated throughout the orders. So THD, or total harmonic distortion, is the measure of the sum of the harmonic components of the distorted waveform. It can be calculated for either current or voltage, and is the root mean square sum of the harmonics divided by one of two values, either the fundamental value or the RMS value of the total waveform. That value is typically expressed as a percentage. Now, when it comes to current harmonics, THD can be misleading. THD is can be referenced by the amplitude of the fundamental. So the voltage fundamental is always there in a non-faulty conditions, but that is not true for current. As the current amplitude fluctuates with the load's impedance, it can go higher and lower. If the current being drawn by the load is near zero, it would appear that the THD would be high. We can see that on this line. So if you have a total harmonic current is 2.2 amps and the fundamental current being drawn by the load is 200 amps, the THD would be 3.16%. Now, if we have the fundamental current being drawn by the load drops to 200 milliamps, then the THD will equal 100%. This is deceiving because the THD levels appear to be high, but this is only because there is little current being drawn. Total demand distortion, or TDD, measurements is what we would want to use for current harmonic measurements. It references the total root mean square harmonic current distortion to the maximum average demand current recorded during the test interval. Therefore, the reference value is the same throughout the test and is a valid value. Some utilities will even have a standard TDD value they use as a reference. That makes it easier for them to compare the TDD values from different recordings. So the power quality industry has developed certain index values caused by the presence of harmonics. As we just spoke about, that would be the THD and the TDD, or total harmonic distortion and total demand distortion. These come from different standards, IEEE 519, the European standard EN 50160. A RVC, or rapid voltage change, is a fast rise or fall in the RMS voltage. Now, these events usually will be noticeable in lighting and not typically bring damage to any electrical equipment. Residential households are usually the most affected, especially in a weak network. So RVC events can be caused by the switching on of a specific load or by a sudden change in source voltage, like solar. With the clouds, we know when the clouds come, it switches them off, and when it goes, it switches them on. So that rapid change creates that. So typically, an RVC event starts with a steep down-going step followed by an upgoing ramp, usually and ending in a voltage that's less than where it started. So the fall time could be very short, while it can take several cycles for it to ramp back up. For an event to be classified as a RVC event, the voltage must not fall below the threshold limit set. If it did, it would then be classified as a dip or a sag. And that brings us to questions and comments.
Thank you. Okay, just as a reminder, that concluded our presentation portion of the webinar, but we're going to move into question and answers right now. And if you'd like to ask a question, you can send it through the question box in your webinar controls. So I'll move on to the first question. What does Megger have to offer for power quality measurements?
So Megger has our new handheld Class A analyzer. Class A meaning its measurement capabilities and accuracy meet the IEC 61000-4-30 and IEEE standards. It can measure and record AC or DC up to 1,000 volts and up to 6,000 amps. It is actually made in Valley Forge in the USA at our Valley Forge office. With this unit, we have implemented an automatic CT recognition and auto connection verification features that only we have. This means you always get good data that you're after, no bad recordings. The unit will actually tell you if you're connected or if your CT is backwards, and give you and allow you to change it and fix it before the recording starts. It's easy to use interface and error-proof software. Basically allow for anyone to successfully make power quality measurements. You don't have to be an expert.
Okay, what does Class A mean?
Well, that's a good question. So Class A is would be an instrument like the MPQ 1000. More and more customers around the world require a Class A certification for their PQ measurements. And this is important because different instruments aggregate their data differently. If you have two different units, you can get two different readings on each one. So there's two classes in the standards, Class A and Class S. And Class S is not held to the as high as standard as the Class A, and should only be used for statistical purposes such as surveys and troubleshooting. And they usually have a limited subset of parameters as well. So with the demand for PQ analyzers increasing, folks buying them should be aware whether they need Class A or Class S. It's very important not to get a Class S when Class A is required.
Okay, does Megger offer any logging equipment to be able to see over time what's going on with the power coming into a building?
Yes, that would be the MPQ 1000 that I just mentioned a few minutes ago. What was the question exactly again?
Of course, I just deleted it.
Oh, but I know I heard it. But it would be the MPQ 1000 would be able to do all that.
It was about logging it over time, logging the measurements over time.
Ours comes with a 32 gig SD card, so you'll basically never run out of space. You'll be able to do it for a very long time.
Okay.
If you wanted to, even one recording you would never run out of space for one recording.
And we offer that through Transcat for the
Absolutely.
listeners. Can Megger instruments measure VARs, VARS, and options to correct high VARs?
Yes, it does measure demand and energy. We can do energy projections. So you can print your reports and charts and be able to see your energy demand and projections.
Okay. How important are high-speed transients? Because on distribution systems, they don't really have an impact.
That is true. They have little impact, if any, because of the long cable runs. So just a few meters of cable will dampen the transients. Slower transients, 64 milliseconds and below, would be more likely to be found in a distribution system. But higher speed transients have impact will have impact where you have limited cable runs, like I mentioned earlier, in like offshore oil platforms, mines, commercial and residential solar. The solar panel output levels change instantaneously because of the solar radiation, and this can cause damage to electronics. Most, like I said before, have input filters, but if they're continuously getting hit, it will over time cause the damage. We have already seen customers losing microwaves and refrigerators, like every 15 months or so. So having an analyzer capable of recording transients down to 1 microsecond, like the MPQ 1000 that I mentioned a few minutes ago, will help you identify the problem so you can take corrective action, save you the time and money on buying and installing new equipment from Transients taking out your equipment.
Okay, I hear a lot about harmonics. What should I really be concerned with?
But that depends on the problem you're having. If you're looking for problems with high neutral currents, you would want to look at zero sequence or the tripling harmonics, because they don't cancel each other out. Instead, they'll add up on the neutral line. If you have issues with equipment like equipment vibrations, you may want to look at negative sequence harmonics, because their magnetic fields are in reverse rotation of the fundamental, and they create counter torque conditions and vibrations. And if you want to see if you see high even harmonics on your analyzer, that would be a sign of a faulty rectifier somewhere on the line. It could mean a diode on a switching power supply failed. In a lot of electronics these days, they have the high-speed switching power supplies, which create higher order harmonics. We can see them as high as the 49th or 50th order. Also, when dealing with solar, you can actually see harmonics above the 50th order. That standards for IEEE 519 and EN 50160, they put limits on the THD, or the total harmonic distortion, and what acceptable values are. So right now we only have recommended limits up to the 50th order, but going forward, especially with the renewable sources, we will see more problems with harmonics higher than the 50th order. And actually the MPQ does can do waveform analysis up to the 128th order.
Okay, do SCR or TRIAC driven loads create troublesome harmonics? I might have mispronounced that. But.
What? Can you say it one more time?
Do SCR, like S like Sam, C like Charlie, R like Ralph, or TRIAC driven loads create troublesome harmonics?
That is a good question. Let me I don't really. I'm gonna have to get back to that one. Can you send me that question and I can get that answer for you? Okay.
Yep, that was from Randy. Randy, we'll get back to you on that. Okay, so that's it for questions today. If there were any questions that weren't answered, you can submit them directly to me at nvanwert@transcat.com, or you can reach us on our website. But definitely, if you have questions that weren't answered, please do reach out to me. And thanks, Jason, for presenting. We hope everyone got something out of the presentation today. And we will be following up in the next few days with a link to the recorded webinar and the slides from today. Thanks for joining us, and I hope you continue to join us for future Transcat e-learning webinars. Thanks, Jason.
Yep, thank you.
Okay, take care.
All right, you too. Bye-bye.